Okay, here we go. All right, welcome to week number 2 of Let's Read Code. So this week, chapters 4 and 5 learned all about electricity. Oh, hey, someone else joined. Yay. So, electricity, it's all about the properties and effects generated by electrons flowing around different things. So, talked a little bit in the book about how atoms are structured and how electrons float around outside sort of a core of protons and neutrons. And as different things happen, chemical reactions or physical interactions happen, electrons sometimes get bumped off and start, maybe going down a chain of atoms and flowing around. And eventually, if you get enough of that happening, you get actual useful electricity. Couple important things about how we measure electricity, how we talk about electrical forces. Volts are electrical potential. So we talk about volts as like how much electrical oomph does this thing have, basically. If you want to think about it like water in pipes, which is a fairly apt analogy, at least for basic electricity things. It's how much water pressure you have in your system. It's not necessarily how much water is actually moving, but it's how much force that water can push on things. So this is sort of the same thing, just with electrical power. How much work can this system actually do? Then amps are the actual measure of flowing electricity in a circuit. So how many electrons are actually moving around at a certain point of time or over a certain period of time. Then ohms are how we measure electrical resistance, or how much fight whatever material your electrical charge is passing through is going to push back against the electricity flowing through it, or put it a slightly different way, how readily available are the electrons floating around in something to get bumped off and move somewhere else. So, enough just talking about things. Let's start playing with stuff. So, the most important tools that we need when working with electronics is the multimeter, which, as you can kind of gather from the name, is a meter for multiple things. So we're going to use it mostly to measure voltage in a system. Attached to the meter, we've got these two little stabby, pokey things that we can hold up against wires or other things to measure what's going on with them. We're also going to use it to measure resistance, or because this is a slightly fancier, nicer meter, we can also use it to check for continuity, to make sure we actually have a complete circuit. So like if I just hold the two things next to each other, it beeps because we have a complete electrical circuit. There's charge that can flow out of the meter through the cord, out of one probe into the other one, and back through the meter. So we'll be using that quite a bit. Book spent some time talking about wrong direction. Batteries. So batteries are basically just containers full of chemicals that react slowly or quickly to produce free electrons and then suck them in the other side. So most of your common household batteries, we're going to measure right here, produce. I hold one, my hand's in the way, you can't really see what I'm doing. Hold one probe against the positive side, another probe against the other side, I get approximately 1.5 volts. Because the chemical reaction going on inside is a little bit fun sometimes. You may get a little bit more than 1.5 volts when it's a fresh battery, and as the battery starts dying, you start getting less and less and less power until it just completely goes away. So, because of all that, I'm actually not going to be using batteries today because they're bad and gross. Instead, I am borrowing the nice, happy, regulated, controlled power supply off of a microcontroller. So this will always be spitting out exactly, or within a certain tolerance, 3.3 volts. It's plugged into the wall and has a bunch of circuitry and stuff inside of this board that changes power to different levels to do the things that we need inside the board, but also that we can steal to use for other stuff. Another change I'm making in our little experiments here, light bulbs are gross and hard to find small ones of anymore that we could use with batteries or power supplies the size that I'm using. So instead, we have light emitting diodes, or LEDs. So a diode is basically a one-way valve for electrical current. So it only lets electricity move in one direction. So if you look at the connections coming off of this thing, you'll notice one leg is longer than the other one. So that one gets connected to the positive side of the connection. The short one gets connected to the negative side. And then if you hook them up backwards, it won't actually work because the diode inside of there prevents the current from flowing the opposite direction that it's supposed to. Then the other thing, breadboards, handy little platforms for doing electronics prototyping. So this board is basically a big mess of wires hidden inside this nice little grid structure. So all of these holes going down the side are connected, and all of these holes going down the side are connected. So this is typically where I'll connect the power supply to enable to supply power to the rest of the board. And then each one of these little rows is also connected. So anything that I plug in here will be connected to anything that I plug in over here, but not to anything over here or over here. So I have set up over here an LED with a red wire plugged into, I'm going to zoom in just a little bit, maybe see a little better what's going on. So I have a red wire in the same row as the long leg coming off of the LED. I have a white wire, the same row as the short leg of the LED. And then if I plug these in to the power supply in the correct place, hey, look, the LED lights up. So that's it plugged in correctly. If I flip-flop them and plug them in backwards, then I don't get any light because, again, LEDs only let the current flow through one direction. So let's talk about telegraphs or telegraph-like circuits. So here, I pre-built basically a very simple telegraph. Works going both directions. Plug my power supply wires in here real quick. So when I push this button over here, the red LED lights up. When I push this button over here, the green LED lights up. So we can actually, like it said in the book, all electrical circuits are circles, so we can kind of go through and trace what's going on. Fun fact, most electrical people think about electricity backwards from most like physics people, because the reality is the electrons come out of the negative side and go around and go to the positive side. But most like electricians or people that do electronic stuff typically think of the electricity as flowing from the positive side to the negative side, which drives a lot of people nuts. So if we go through and trace this thing, I've got a white wire connected to my power supply. That's in the same row as this green wire, which is going over here. It's in the same row as the short leg of my red LED, which is connected to this other green wire, which is connected to my button, which is then connected to the red wire that goes back to the power supply. Which means when I hit this button, it turns on, because when I'm pressing the button, it's basically connecting this red wire and this green wire together. So, like it talked about in the book, we can tie all of the ground or the negative connections together into a shared common ground thing. In our case, it doesn't actually save us any wiring, but if you were actually doing this, running this between your house and your neighbor's house, it would totally work and save you a very long run of wire. So thing still works as expected. So kind of go see why and how it all works in the diagram in the book. I could also, if I wanted to get real fancy, and go use a bunch of aluminum foil or go buy a bunch of copper or something, I could also basically eliminate some more wires, like it talked about again in the book. If you were doing this at real people like house or real telegraph scale, burying a very large copper pipe or something in the ground to connect your things to. And instead of using the negative side of your battery directly, you would connect the negative side of your battery also, to the ground somehow, and use the entire Earth as your sink of electrons or your source of electrons to run everything. So that's basic electricity 101 and how a simple telegraph circuit works. Does anybody have questions, comments, things they want to see me try with the mess of wires and buttons and LEDs I've got sitting in front of me? No? Nothing at all? This is going to end up being even shorter than last week.
We played with a lot of these things when Beckett was smaller and snap circuits, although we haven't really used breadboards.
Sure.
I guess like when I was reading the book, I always thought of ground as like a safety thing and kind of dispersing the electricity, not thought of it as like another way to complete a circuit.
Yeah. So the way when we're talking about like house wiring, the ground works just a little bit differently, because in some sense it is a safety thing. Like the third pin in your electrical outlets basically is if there's like a short circuit inside of your appliance or your lamp or whatever it is you've got plugged in, instead of sending all of those extra electrons racing around inside of whatever you've got plugged in and heating up and catching fire or exploding or something, it's instead going to dump all of that into the ground. so that you have less problems and less fire, which is always a good thing.
And also, this is like a DC circuit, whereas home is AC, so it's a little bit different.
Correct. Yes. So I actually forget, I haven't read super far ahead in the book again to review for things. I forget if we talk about the difference between direct current and alternating current, but that's a fairly important thing. So all of this stuff that we were just looking at is what we call direct current. So the electrons are all actually moving in a circle. Like you could, in theory, pick out an electron and watch it drive around the entire circuit, right? So alternating current is a slightly different way of running an electrical circuit where instead the electrons basically just sit in the same place and bounce back and forth. So you still get the electrical force out of it and voltage and current because everything is still moving. It's just moving back and forth. So it has some advantages and some disadvantages, most of which you'll learn about at some point in science or physics class or something. Lots of big debates back when the whole like national power grid started being a thing that people were thinking about, the great Edison versus Tesla debates about, oh, which one's safer, which one is more efficient, which one is less likely to kill somebody if you grab a hold of two ends of a cable, or, you know, try and electrocute an elephant or something. Fun stuff. Go read about it.
Well, I know I've seen the movie, I guess, about them trying to kill the elephant, but I was surprised when in the end of the book they just end it with like trying to have this super long cable, and they didn't mention alternating current and how that eliminated that need for the super long cable.
Right.
Although I think you can kill an elephant with DC as well.
Yes, you can.
Just slightly different.
Yeah.
The main thing AC is that they can use transformers and just kind of raise the voltage a bunch, send it over a long distance, and reduce it down to the voltage you need at home, for most homes at least.
Correct.
That's the big deal. But like now with like solar panels and stuff, those are all DC. So you have to have things like inverters to convert the DC to AC so you can use all your appliances, but all of your appliances use DC usually, so you have to use AC, convert that to DC.
And convert it back to DC.
Yeah. Electrical power systems are fun. And by fun, I kind of mean gross sometimes. That's why I stick with the little tiny stuff and not the house-sized electrical system design. Let's see, what other things in the book that I could need to hit on that would be useful to know for later?
I also didn't realize, and I probably should have, the like batteries in parallel versus in series, and how like one 1.5 another was 3 because you could take the combined power of the battery.
Right. Yeah, that's a fairly important concept. So like a lot of the details about how much current does a certain battery or power supply generate, how do we measure that kind of stuff, isn't super important for most of what we're doing, unless you actually want to follow along and go buy some stuff and build a computery thing like we're going to end up doing. So just kind of give you an idea of what's coming up in the next few weeks. Next week is probably going to be another, I'll have some circuity things to play with set up here. week after that, we'll start getting into a couple of like simulator programs instead of me actually having to go find and buy stuff, or you all having to go find and buy stuff. Have one actual digital circuit simulator program that I'm going to show you that you can go download for free. And also we're probably going to play Minecraft a little bit because you can do a lot of this stuff in Minecraft. So I'll show you how to do some of that and also show you a mod that makes it so much more pleasant to play with, because Redstone out of the box is gross.
Okay. We have lots of Raspberry Pis.
Yeah, because if I was actually going to follow along and build something like what the book kind of walks you through building, which is something I really want to do one of these days, I would actually probably end up cheating a little bit for one piece of it and not actually go build the circuit that would be easily the size of my office if I wanted it to actually have a useful amount of memory and storage space, and instead probably just hook up an Arduino or a Raspberry Pi or something and cheat a little bit. But yeah. What other questions or discussions can we have? Because I just flipped back through the book again, and I think I hit on all the high points.
Is Ian all knowledgeable about this?
Not really.
Have you worked with
Did you learn anything?
Not all kind of. We're covering it in science class right now, so just like, this seems familiar.
Yeah, we don't have really like an electrical sub team on the robotics team.
Yeah, it's mostly just programming people and someone, oh hey, that probably needs to plug in somewhere.
I wasn't sure how unique we were with the snap circuits and the Arduino and the Raspberry Pi stuff, if that's like a common kid thing to do these days.
I mean, it's getting slightly more common, but I still wouldn't call it a super common thing.
I've played with the snap circuits.
Yeah.
When you were younger?
Oh yeah.
Do you have any experience with Arduino or Raspberry Pi?
No. I have a few friends who do though. They tell me about it. So
it's like
so
similar.
that's the other thing. I'll probably because I'll go post like the recording of this on the website, and I'll probably put together like a little shopping list if you want to go buy some of this stuff and learn how it works and play with it on your own.
Cool.
Yeah. Yeah. Turn you off. My multimeter beeps at me if I leave it on too long.
It's a heavy feature.
So are you going to get into like using the multimeter, measuring ohms versus voltage, or?
A little bit. So here's what we can do. We can go ahead and show that a little bit. Wrong button there. Okay. So basically the way this works, most multimeters have this little dial thing on it that lets you choose just exactly what you're measuring. I was using mostly DC voltage, so the V with the line over it, as opposed to the V with the squiggle over it, which would be your AC voltage. So this is how I grabbed the battery, trying to put this in a place where you can actually see it. I'm gonna back out. Guys. So I grabbed the battery and measured it like that. The thing we can do, this little symbol right here is the usual symbol for measuring ohms and resistance. So for example, if I go grab out of my box of random electronicsy nonsense and go grab, focus.
Yeah, the resistor.
So it doesn't really want to, my camera's being dumb. But this is a resistor. So this is a little hunk of metal and ceramic and other who knows what that is built to have a specific amount of resistance. So you can't really see real well because my camera won't focus. That's better. The main body of it is it has these colored bands on it, which if you actually take the time to memorize what they all mean, will actually tell you what this or how much resistance this thing is supposed to have. So again, if I hold the probes up against the resistor, we can see that this is a 0.975 ohm resistance. Let's see. I can grab another one that I'm checking to make sure is actually going to be different when I read it. So different colors on this one. And this one is jumping all over the place. And settling out at 4.6. So if you go back to the book,
Brad.
yes.
So what does this wait, if I can, this symbol mean?
Hold on. You can't see. Okay, there it is. So I think so. Is that
So like
that
the
symbol right
triangle
there?
one? Oh yes.
Oh, the triangle-y one. Yeah, the triangle-y one that looks kind of like a sound wave or something like that. So that is the continuity tester I was talking about earlier. So if you put it on that and like either you touch your probes together or you shove it in inside of a complete circuit somewhere, which I can't really do because everything is buried inside of a breadboard right now. But that will show you if your circuit is actually complete or not, or if you've got something in the way or disconnected.
Okay.
Yeah, so that's a very handy thing. And then I also have this other kind of in the same place little triangle pointing at a line thing. So this is the like electrical symbol for a diode, if I remember correctly.
Okay.
So I think that, I'm not sure just exactly what that does. I've never tried. I'm going to grab an LED and find out.
Like the wall kind of signal that it's only going in one direction and will be stopped the other way.
Yeah, so I think it's measuring something across this LED. It's too big of a number for it to be the amount of like voltage it's eating up as the current goes through it. I don't know. I'll have to go look that up later. Also just realized I was zoomed in too tight and you couldn't see what I was actually doing. It's okay. You didn't miss much. I was holding the probes up to an LED and it was displaying a number, approximately 1.7, which is not sure what exactly that's from. What else do I have on here? So again, we can measure AC volts. It also has a separate thing for measuring the AC millivolts. So for measuring very, very small amounts of alternating current. Honestly, not sure what that one is. Then Hertz, which presumably would measure the frequency of an alternating current signal. So again, in alternating current, your electrons are just bouncing back and forth. So that would measure how quickly those electrons are moving. And then you can go get big fancy multimeters that measure 200 different things. But this one does what I need it to do, so. All right. What other basic electricity questions do we have? Anything? Anything at all? No? Cool. So next week, you get to see if I can manage to successfully build an electromagnet or not, and try and actually build a telegraph. So that'll be fun. And what's coming up after that? Good question. I need to read further ahead in the book again. After that comes binary, and then getting into logic gates and starting to actually build things that start to look like pieces of useful computing equipment. And then we start putting those together and putting the things we make out of that together and assembling and assembling and assembling things until we end up with something that can actually, you know, compute.
Ooh.
It'll be fun. So again, if you want to buy some stuff to play around with, I'll post a shopping list on the website along with the recording of this video. And I'll see you next week.
What do we need to read for next week?
Oh yes, for next week, the next 2 chapters, I believe. Go look real quick. Yes, chapters 6 and 7.
Okay.
So talk about electromagnets and relays, and start talking about binary